Okay, so the Ryans are away. So let's watch this here, or let's record this here. So yes, as I was saying, you're both going to love me and hate me. You're going to love me because I'm going to make vectors easier, and you're going to hate me because you're going to realize if I'd only done that last year, it would have been a whole lot easier to spend. So in the same breath, you're going to both love me and hate me. Allow me to demonstrate. To add vectors numerically, here's the new way. I'm going to remind you of the old way. I didn't hand you any of this. You just have to sit back and watch. I'll tell you when you want to start writing. Okay? Do you see these vectors here? Do you see this vector A and this vector B?
Yeah.
Okay, well, vectors, if you place them on a regular Cartesian grid, you know, your X and Y grid, you could call this vector here, instead of talking about the length of it and its direction, if you labeled it with how long it was this way and how long it was this way, it would be like 7 and 4. You could represent it with a 7x and a 4y, right? And you could represent the green one with a 5 over and a 14 up. And if I add them together, watch what happens to the two x's. All I did here was I had a red 7 and a green 5, which makes my resultant an x value of 12. And here my red y was 4, and my green y was 14, and I added them together and I got 18. No rulers, no protractors, no nothing. I'll show you more right away. First of all, let's go back in time. On page 80, there's a question about adding vectors. You can look up page 80 if you wish. In grade 11, you added two types of vectors. So you had two types of vector questions, right? Vectors at right angles to each other, which we use Pythagoras to solve. Remember, a squared equals b squared plus c squared, right? All that jazz. And we also had vectors not at right angles to each other, and we did them by scale drawing, right? Remember how much fun that was? Not so much. If only there was an easier way to do it. Here's an example of a scale diagram one, right? You had to go like this and get your protractor out and go like that. And like, how long would this take you? It might.
Too long.
And you would likely make, even if you were extremely careful, you might make a small error on this one, and a small error on that one, a small error on that one. It might actually magnify, right? If only there was some mathematical way to do it. There is. I'm going to turn the components off. Okay, so you go back there. These are three vectors, A, B, and C, right? And when I add them together, I'll put it right there. I go A, then I go B like so, and then I go C like that, right? Okay, now let me show you the components. If I take the x component of A, the how much does A go sideways? And I'm just going to pull that out, okay? Right. And I'm going to pull the bx out, and I'm going to add it tip to tail like so. Then I'm going to take the cx, and now you'll notice that it's negative, so it's got to go, I got to go tip to tail, so it's going to go like right there, right? Okay, now what is the resultant x? Well, it's that little bit right there. I didn't draw it very well, but it's more or less that little guy right there, right?
Yeah.
Okay, so I'm going to pull that off to the side, and that's our resultant x, right? And now I'm going to take out the y, the ay, and the by, and now the cy is also up. I'm not sure why it's green. And what would you say is the resultant y? And now I'm going to take my x resultant and my y resultant, and I'm going to add them together. And what do I get overall? I get that one right there. Now, is that one right there? Riley's head just exploded. What about your head, Riley? Did it explode? He smiled, yeah. Okay, Big deal, right?
Yeah.
Big deal. But it's kind of cool. Now, is there a way that we could, if I knew this number, like if I knew that A was like, say, 30, and I knew this angle, is it reasonably easy to come up with that side and that side? Yeah, because you've got the hypotenuse and the angle, and you can find the adjacent and the opposite, right? So you could find out numerically what AX and BX and CX are. And now, are the X's always going to be like right and left? They have to be, because that's by definition, right? That's the X. So if this was, say, if the A here was like, I don't know, 8, and this B was like 2, and that C was like minus 12, what would the overall be? You can just add them up with no protractor. It would be 2 plus 8 is 10, minus 12 would be minus 2. And could you do the same thing for the Y's? Absolutely. And then will you always get an X that is perpendicular to a Y? Will the X always be perpendicular to the Y? It has to be, because that's the definition of X and Y are, right? And then you can always use Pythagoras. So basically what we're doing is we're taking these kind of questions and turning them into Pythagoras kind of questions. That's sort of the steps. Now, some of you might say, whoa, too much information, don't get it. No problem, I'm going to show you detailed steps. Okay, but that's basically the idea. I wanted to show you the sort of the picture version. Here's where you want to start writing stuff down. Okay, so find page 80, because we actually have to find the question. It's actually the bottom of page 81, and I don't actually have the question written out, so let's just sort of summarize this question on the bottom of page 81 just for our notes here, okay? So we got a student runs to school covering a distance of 0.5 kilometers in a distance given by north 20 east. So I'm just going to say vector 1, I think I used the expression D for displacement later on. Let me just double check. Yeah, I did. Okay. So I'm going to say that vector D1, displacement 1, is 0.5 kilometers in a direction of north 20 east. And again, this is page 81 in your book. She then trudges over to her friend's house 0.3 kilometers away, due west from the school. So D2 is 0.3 kilometers at due west. And then there's a third displacement to the mall, 0.8 kilometers west 57. I think if you just get those three down, that's all you really need. Basically what they're saying is, here's three vectors, let's add them together. Does everyone know what we're doing?
I'm not sure where we are at all.
I'm on page 81 in the textbook.
I don't see that triangle.
You won't yet. You won't see that triangle. I'm not even sure why I've got that triangle there. Yeah, just ignore that triangle. I'll get rid of it. There. Bottom of page 81 is the example, and those are the three vectors that come out of that question, Steve, right? And now I'm basically just going to ignore the textbook because they do a lousy job of explaining it. And I'm going to show you Bannett's method of adding by components. Okay? Now, back up here. What did I do? I said find the x and y components for this vector, find the x and y components for this vector, and find the x and y components for this vector, right? Let's go ahead and do that. Has everyone got this down? Anyone still working on that? Okay. So, step one, find the x and y components for each vector. So what did I do? I drew vector 1, and you'll remember that vector 1 was 0.5 at north 20 east, right?
So we should have to
No. Does this need to be to scale? No, we're not using our protractors at all. Just a sketch sheet. Okay? So all I've done there is drawn out the picture. Here's D1 right here. Here's 20 degrees. And I've shown, I want you to show the components. You might remember in grade 11 I taught you just draw that little reference line. Right? Remember me doing that? I want you to actually complete, not complete the square, because no one likes doing that. Complete the triangle. And label them. I'm going to label this D1. This is vector D1. This is D1Y. Why is that the Y? Because it's up and down. And this is the X because it's left and right. And then find the X and Y components. D1X is 0.5 sine 20. Jason, why is it sine 20? Opposite side. This is opposite to the angle, right? And opposite is sine. When I say opposite to sine, everyone kind of knows what that means? So it's 0.5. This is 0.5 times sine 20. Will the X always be the sine? Yeah, you and Hannah are both right. Did you know why, Hannah? Did you know why it's no? You're right. It's no.
Yeah, I just took recall.
Oh, okay. So, like, if I had my angle down here, which would then be 70, right? This would be the X and this would be the Y, but the X would be adjacent to the 70, right? So there are some students that want that rule. They want, oh, X always to be sine. It's not going to happen. Okay? I'm trying to go slow and deliberate enough here. So I got 0.5 sine 20 is 0.17. The Y then is going to be 0.5 cos 20. If 1 is the sine, if the X is the sine, is the Y always going to be the cos? Yeah, like both of them can't both be sine, right? Both of them can be the same number if it was 45 degrees, but. So I got 0.5 cos 20 and 0.47. Let's move on to vector 2. Here's vector 2. Do you need to draw the picture for each one? It sure helps. It's doable, not advisable. I would do it. I'm not going to say you have to, but you'd be a fool not to. So, yes. I will call you a fool if you don't do it. So, don't do it at your own peril. So, D2 is not a triangle because it's due west, and so what is the X value?
Negative.
Now, it was 0.3 kilometers. Why is it minus 0.3? It's going left. Right you are, right. What is the Y value? Why is it 0?
It's not going up or
Because it
down.
doesn't go up or down.
Flat.
Everybody with me so far? More or less, right? Yeah? I'll go back, at the end of all this, I'll go back and I'll sort of summarize the steps again. I have to do this now for the third one. The third vector was .8 west 50 south, right? So there's west 50 south and 0.8 long. There's my X and there's my Y. Okay, so Steve's question is, do you have to draw the triangle that way? Basically what you're saying is, could I draw it like this? Yes, absolutely you can. But remember that the initial question told us west 50 south, right? So you sort of end up west 50 south. Okay, well I'm going to draw west, and then I'm going to go south, right? You could do this, but you'd have to be careful that that angle then would be 40 degrees, not 50, right? So yes, entirely okay. Well, go ahead and do it. It just isn't sort of the comfortable way to do it, that's all. Like it doesn't sort of lend itself naturally that way, that's all. Okay, so let's do the X first. D3X is going to be adjacent, so it's minus 0.51. Now I don't really care too much whether or not you put that negative sign right there. But how important is it that the negative sign goes right there? Why is this negative here important? Because it's going left. And does that matter that it's going left and not right?
Yeah.
It's huge to the question, yes. So that makes a big deal there. So make sure that those are nice and clear. The y then is going to be 0.8 sine 50, and again, because it's down, minus 0.61. Okay. Basically, all I've done is find the x and y components multiple times. I've done the same thing over and over again, haven't I? Right? What's the next step? Exactly. Let's go back to our original sort of picture one here. I took the ax and the bx and cx and I added them together. Now, because they're all collinear, they're all in the same straight line, it's easy to add them. Right? So, the resultant, don't worry about this picture here. I write Rx, standing for the x component of the resultant is the x component of D1 plus the x component of D2 plus the x component of D3. That's what that stands for. So add up those x components, 0.17 plus minus 0.3 plus minus 0.51, and you get an x component of minus 0.64. The next step then is to add the y's. I've added the x's and I've added the y's. I now have the x component of the resultant and the x component of the y. So I'm going to draw this picture. There's my Rx. How do I know to go to the left? Minus 0.64. How do I know to go down? Minus 0.14. How important is this picture?
It shows the direction.
It does, right? Could you do it without? Yeah, you would know that minus 0.64 is to the left and minus 0.14 is to the down. But when it comes, it's doable, but again, not advisable. I highly recommend drawing that picture. And I think as you do it, you'll go, yeah, you got to do that, right? Okay, are we in the home stretch now?
Yeah.
I've basically turned this into a Pythagoras kind of question, right? So what's the next step, Hannah? Don't know? I'm trying to find that one right there, right?
Freak out.
So there it is there, right? And I just redo the picture on this next slide here. So I wrote r squared is equal to rx squared plus ry squared. Do your basic grade 9 Pythagoras, 0.66. Do your basic grade 9 inverse tan, 12 degrees at west, 12 south. I'll let you copy that down and then I'll go through it step by step. Okay, so the question is, how do I know it's west 12 south and not south 12 west?
Yeah.
Okay, so the angle, we know that the angle has to be this one here at the start of the resultant, right? Okay, well that line is west, right? Only one of these will be either north or south or east or west, right? So it goes west and then south, so it
Okay,
goes.
just because it goes west
It's
first,
because it goes west first, I guess you could say, yeah.
or because it's more west. We can't really see that.
You're right. Is this to scale? No, I mean this is much smaller than that, right? So it really should be like somewhere about there, I guess. So what are those steps again? I think is what my next. Yeah. Okay. Oh, sorry.
That picture said.
Yeah. You're a fast reader, Steve.
Reaction time is just through the roof.
We say
I think that is that funny?
Oh, yeah. That's good. It's all right. It doesn't really crack it up.
No, it's not a knee slapper or nothing. Let's go back and let's just. Should we write down the steps as a group?
Yeah.
Should I write it on the board?
Like with actual numbers or just?
No, steps. How to.
Good. That's good.
Let's do it. Ryan at home won't be able to see it. Ryan or Ryan. I could just write it over here, I guess, right? What's step 1? Find the x component. Find the y component. right? Repeat as needed, right? Find the x component, find the y component, repeat as needed, however many vectors you got. Then what, Riley? Not yet.
Add them together?
Add what together?
The x's together and the y's together.
Yes.
Not actually together.
Yeah, add all the x's together.
And the y's.
Add the x's. Add the y's. Don't forget about the positive and negative. Directions matter. Good point. Step 4 would be then,
Make find the triangle.
I guess, draw the picture. Draw a picture. Solve by Pythagoras. Solve the angle. Solve the theta. I don't know. I don't think it's that many steps, Steve. When you break it down like that. Did I tell you guys? I think that was my grade 11s I told. When I was on a Mediterranean cruise 5 years ago, we were going along and there was this island, and the captain says, I don't know, tour guide or someone says, that island over there is the birthplace of Pythagoras. And I thought, oh, that was pretty cool. And I was the only person on the boat that was interested, oddly enough. Yeah. And you know what? I told that story to my grade 11th, and Lane Stockton said exactly the same thing. That happens to you a lot, Mr. Ben. Well, that's just me, I guess. Yeah, I thought it was kind of neat. Oh, Pythagoras was born over there. Whatever. There's your steps. Relatively easy, right? You're probably wishing, oh, I sure wish I could practice that.
Is homework fresh?
Right out of the oven. So, question, or page 1 here, did I miss you? Sure, can you give me 30 seconds? Page 1 is just find the components, that's all it is. There's 5 of them. Do you have to do all 5? Page 2 is add by components. There's 4 of them. You need to do them all?
Is this like all the separate steps then, basically?
Well, page 1 is simply find the components, which is just step 1 on our board, right? Find the x and y components.
That's without adding them together?
Without adding them together, right? So that's all the front page is. Just find the components. Page 2 is vector addition. You'll notice that in each case, oh no, that's not true. Case 1, 2, and 3, there's 2 vectors. Case 4, there's 3. And I don't know what the difference is on the next page. I think they're just slightly harder, maybe. I don't know. So you've got lots of questions to do there. Oh, there's a QR code to get to the solutions, but I didn't actually put the link itself there, I guess. So the only way to get to it is to scan it, I guess. So, but the solutions are there. I also have these, and they are available, as always,
In the red book.
white binder. Grade 12s get the white binder. Okay, so if you want to check your answers, you can check in here. I'm giving you the rest of the period to practice on those. That, my friends, is really it.
Yeah.
Like, there's not a lot. I'm going to give you some days to work on vector stuff, but that's really all I got to do for this unit, yeah. So we'll have to talk about a test real soon.